So the left side has a small d, so it has to have a bigger force. The right side has a bigger d, so it can get away with a smaller force. Does that make sense?
Yeah.
I can see you're all really enjoying
What'd you
physics.
learn about physics today?
Yeah.
D's!
Yeah. If you have a small d, you gotta have a big force.
Exactly. That's how I
If you got a big d, then you can get away with less force. Okay. So that's what it boils down to. The torques are the same. The torques have to be the same. The forces do not have to weigh the same. So other examples of torque. This is great. If I was to throw this at you, what you would notice is it spins over its center of mass. The center of mass of a hammer is pretty close to the big metal head of the hammer right there. Okay? So if I was to throw this, it would spin over its center of mass. In fact, there's actually cool pictures online and some videos where someone has done that, and they actually painted a little dot here, and you can see the dot go dot, 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 while the hammer is spinning, because it spins over its center of mass. But if you were to cut the hammer in half right here, which side would weigh more? The metal head or the handle? Yeah, the metal head would, because you have a much smaller d, so you have to have a bigger force. Same thing with this one. This one I actually can throw, but I don't want to go outside. This one I'll put a hole in the concrete. That and I really like this hammer. Okay. Oh, fun fact. Bowling balls. Is there center of mass in the very center?
No.
Any bowlers in here? Gotta be one or two.
No, but we learned.
Yo, where's the bowling?
That's what the bowler.
Okay, so Spencer, is the center of mass of a bowling ball right in the center of the sphere?
No.
No. Why?
Because you want it to be able to like rotate around like a point that's near like the front of the ball kind of, and so then it can get more like drive kind of.
Yeah. So if the bowling ball's center of mass was right in the center, even if you spun it with a really crazy amount of English, it would still mostly move in a straight line. So what they do is they put the bowling ball center of mass where you want it to be. You buy a bowling ball customized for how much you want it to curve, whether it's close to the holes or away from the holes, and that gives it more English, that gives it more spin, so it actually falls over itself. Mark Rober, who's basically a heroic level engineer, he basically created a bowling ball that has a changing center of mass. It's like BB-8. Have you seen the models for BB-8?
Yeah.
It's basically a bowling ball with a motor inside that rolls the bottom of it, so that rolls the top, so it basically rolls it. So he basically made a BB-8 that has a changing weight inside, so you can roll it and then you can kind of adjust where it goes. Check it out on YouTube, pretty cool. Okay, two-dimensional center of mass. You can ignore this. We're not going to do two-dimensional center of mass. This is called system of particles, and I'm not going to do it until AP. Yeah?
That guy that he did that, so did he have to make like a full motorized system that adjusted it inside the wall as it went? Or was there like some cool like thing that he used that allowed it to change?
Well, here's the thing. All he needed was a simple axis motor to move a weight. So it was in the ball like this. Pretend that's in the center. So he basically allowed it to move here to here. So that changed the center of mass from here to here. So basically he just had a ball that with a rolling motor inside, and as he rolled the motor, the motor could basically move this way, and it changed the center of mass and move this direction, or move it back and move it this direction.
So if you were to split it open, then you would see inside there was a little motor system and a little gap between all the material.
Mm-hmm. Yeah, it wasn't solid. But it was super awesome. Again, YouTube. Learn all sorts of cool stuff on YouTube. Okay, so torque practice, this is for you. You got, so here's Thane at 70 degrees, or 70, so there's Thane. Did I tell you spell your name?
Yeah.
Okay, so there's Thane at one end of a board, and here's Chloe over here at the other end of the board, less than half Thane's weight. Also, maybe Callie. I'm like, who was the smallest person in class? So Chloe or Callie. Anyway, so what's this distance right here? If this is x and this is some other x, what's this distance? See if you can figure it out. That is the fulcrum. Yeah, that is the word we use, the fulcrum. What is x? I'm going to turn the lights on so you can work. What is x?
Oh, like how far?
How far is x? Yes. if the distance from Thane to Chloe is 10 meters, what is x?
Force times distance. 5 on the scale. It's the fulcrum. You mean for wait. So this one is 700 times x equals that equals 300 times 10 minus 10. I feel big break.
I'm giving you this now so you can work on it over the break. It's not due until next, or over the weekend. It's not due until next weekend, and I will talk about it a little bit later, but it's something to get started on. Set it aside for now.
So, oh, I saw this thing
Yeah.
last year.
Last year, all the mobiles that are hanging from the ceiling.
So we can make it out of anything, right?
You can make it out of anything. One year, somebody made it out of metal tools. I had to hang it from the eye wash. It's the only thing that could actually support it. But yeah, it was like clang, 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 all these giant tools, and like, don't walk under it, you're gonna kill yourself.
Wait, is that mine?
He means any. Got
Let's
it.
make it out of anything. Let's avoid the human body parts, and let's avoid candy
Damn, I just got
for some obvious reasons.
I got it. It's okay.
The ants might grow off the way.
Exactly. Yeah. And as cool as it would be to watch the ants crawl down the strings onto the. That would actually be really cool to watch the ants crawl down the strings.
I got a
onto the
better
candy.
idea, Mr. Myers. Ant traps.
Yeah. Why not? But let's just keep that premise. So no candy. All right. So
Ant trap.
in setting it up, hopefully you got the general idea that Fane's torque had to equal Chloe's torque. Now, in this class, listen very carefully. In this class, the board does not matter. Okay? The board itself is considered to be massless. When you go to college, or if you take physics AP, that's not going to be the case. When you take physics AP or when you go to college, the board itself will actually play a role. There will actually be a torque of the board here and a torque of the board in here. But in this class, all the boards are massless. So, I didn't even realize that could actually happen. So 700 newtons times x equals 300 newtons times 10 minus x. Did you solve it? So that's 700x equals 3,000 minus 300x. Is that about, am I mathing correct? Okay, so this is 1,000x, if I add both sides, equals 3,000. Is that the right mathing?
Yes.
Okay. So that means x equals 3 meters.
Okay.
Which would make sense because that's 2,100 newtons on both sides. We can always check our work. That's 2,100 newtons on both sides. 3 times 700, 300 times 7, 2,100 newtons. Sorry, newton meters. 200 newton meters on both sides. Are we cool with that? Shall we move on? Okay, give me a thumbs up if you're like, at least you understand where that number came from. Okay. Wave your hand around if you want me to explain it again. Boy, is this one we can do. We got an apple, so here's the fulcrum right there. We got an apple that is 10 centimeters from one edge. We got an orange 30 centimeters from one edge. The fulcrum is 40 centimeters away. A hand is pushing up at X centimeters away from the edge, and the bread is over here 70 centimeters from one edge. Hoy! Can we do this?
I believe.
We can, because equilibrium has the formula sigma torque equals what? The sum of all the torques must equal, starts with a Z, and it's not zebra. Zero. The sum of all the torques must equal 0, which means the torques on all the left side, the sum of all the torques on the left, have to equal the sum of all the torques on the right. The sum of all the torques on the left have to equal the sum of all the torques on the right. And this is something we can do, but we can massage this a little bit, depending on how we want to do this. One way is we can say how far it is from the fulcrum and make everything positive. The other thing we can do is say, all right, we have positive and negative vectors. We have downward, 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 downward. We have positive and negative vectors to calculate, depending on how we want to do it. We can say, all right, this pulls down, but this pulls down on the other side, so this must push up. Should we work through it? Okay. Hey, Talon, can you see if the camera is capturing this side of the board? It doesn't move it a little bit.
Wouldn't the hand become the fulcrum though?
No, the hand is supporting, keeping it all keep it all from falling. So all the torques on this side are equaling all the torques on this side. Does that make sense?
The original fulcrum.
The fulcrum's right here. Yeah, this little X thing there, that's the fulcrum.
I just, it's like, you see the hand pushing up, and like, I see the 7 Newton bread on the very end giving it like the most possible like force, and then like you have the others on the left that aren't on the, that don't weigh as much in total, and aren't as far out, but I feel like the hand pushing it up would then return that into the fulcrum, so I guess.
Okay. So when I say left and right, what I'm really going to be talking about is clockwise and counterclockwise. So let's look at the apple. If the fulcrum is 40 centimeters away, okay, you know what? We don't have a lot of time. So we're going to come back to this again, and we're going to do it one way today, one way on Monday. So the apple is got 1 Newton, and that 1 Newton is acting 30 centimeters away, 0.30 meters. Can you see that? And it's acting down this way. Then we have the orange, and the orange is 2 Newtons, and it's acting 10 centimeters away, 0.10 meters, and it's also acting down like that. So far, so good? Okay. Then we have the bread. This equals, the bread is 7 Newtons. That's some heavy bread. Must be healthy. Lots of nuts in there. Whole grain. And it's acting 30 centimeters away from the axis. Okay. So it's acting 0.30 meters away, and it's acting down this way. So far, so good? Then we have the hand, and we don't know what the hand is. We're looking for X Newtons, but it's going to be acting, oh, we don't know where it is?
It has to be applying the force of like 13 to like keep it all up.
Well, basically what we need to solve is the torque. So we're just going to leave it as the torque. So we're just going to leave it as the torque of the hand. So that's what we're going to solve for. Are we cool? Or is that 3 Newtons? No, it's applying 3 Newtons. Okay, go back. We are looking at 3 Newtons. We're looking at 3 Newtons, and we're looking at X meters. And it is actually applying its torque up. Okay, so far so good? So, this one is counterclockwise. So there's the fulcrum right there. That's the fulcrum. This one is counterclockwise. This one is what? This one's clockwise, and this one is counterclockwise.
Oh.
So you might think, if you look at this, you kind of imagine this. Does it make sense that the finger is acting in the same direction as the apple and the orange? Because So the apple is pulling it down this way. The orange is pulling it down this way, and the hand is pushing it that way. Does that make sense? So we have 3 vectors producing a torque that is counterclockwise. And we have only 1 vector that is producing a torque clockwise. Make sense? So what should we do with this hand vector?
Do subtract.
We need to make it negative and move it to the other side. So we're going to make this negative and move to the other side. So we're going to have all the clockwise vectors, which is 1 times 0.3 plus 2 times 0.1 plus 3 times x equals the only clockwise vector, which is 7 times 0.3. Now can you solve for x? So 0.3 plus 0.2 plus 3x, is that right? 3x? Yeah. Equals 2.1. Is this math you can do? I can't do it in my head, maybe you can.
Okay, got you.
We'll see if the diagram makes sense to us.
Wait, you subtract. I'm guessing right now.
0.53?
No, but that's 0.57 meters, so it's more or less on the opposite side. Wait.
It's a negative on this side, so.
But that's like in the 50s, 53 centimeters?
33 centimeters?
Perhaps.
So that would be 23, so 53 centimeters. It's gigantic.
Well, the 70 is for the bread and the 40 is for the fulcrum. So I guess 53 would be in between those.
But I'm measuring from the fulcrum.
Oh, I'm not.
So it's like this hand actually should be way the heck over there. But the math makes sense.
Yeah.
So you have a point, let's check our math. 1 Newton, 0.3 meters that way. Yeah. 2 Newtons, 0.1 meter that way. Okay.
But it's like
3 Newtons at some distance over there, and then 7 Newtons the opposite direction, which is right. So 3x, 0.53, 0.3, 0.2, 3x, which is 3 Newtons by some distance, okay? And 2, which is 7 times 0.3 is 2.1. So yeah, diagram is garbage, but the math works.
Well, isn't it measuring? Well, I was on the left side. But
No,
yeah.
I'm measuring everything from the fulcrum.
Oh.
Yeah, I'm measuring everything from the fulcrum. Now tomorrow, we can actually measure everything from the end. We'll put the fulcrum over here and see what happens. And hopefully, we'll get the same answer. Talon, can you press the button, please? Okay, questions?